Okay, we're ready for another application of decay functions, and now we're going to talk about Newton's law of cooling. So what this is a formula that describes cooling. So maybe you have a bowl of soup and you put it on the counter and you let it cool. That's what this formula is going to be talking about. Here's a picture graph, kind of a visual of what's going on here. You have a temperature that starts kind of high up here, and as this might be your time going along here, going along the bottom, and then you have big T would be like your temperature, so this would be your the temperature of whatever that material is, if it's a coffee or if it's soup, something like that. Your temperature is going to actually be going down, and eventually it's going to level out to what your room temperature is. So your room temperature is actually kind of like a horizontal asymptote. It'll come very, very close to that, but never actually come to the room temperature according to this model. So that's kind of how it works. Now the reason why we don't have a linear thing, we don't have a linear relationship here because it's going to actually do a lot of its cooling in the first few minutes, and then eventually it's going to take a lot longer for there to be a significant temperature change after that. So that's why we have this kind of graph, and it's going to be falling. So because it is falling, when we have our cooling constant here, the cooling constant must be negative, so your K has to be negative in order for this particular formula to work. So let's run through what each of these variables mean. The U of T, that's your temperature after cooling. It would also be your temperature at whatever time that you put. So U of T means that's the current temperature or temperature after time T. That's what this would represent. So after cooling is done, that's what the current temperature is. Okay, then your big T, it appears twice in your formula. That's the temperature of the surrounding atmosphere. If you're in a room, it would be room temperature. Sometimes you put a thermometer into a refrigerator, and then the refrigerator itself would be the surrounding temperature. That's what's around the actual thing that's cooling. The U of 0, that's mu sub 0, that's your initial temperature before cooling. So that goes here, so that would be what your original temperature is. That would be maybe something up here when the timer starts. That's where the temperature actually is at that time. Our cooling constant we talked about, that has to be negative, and then we have our T, which is going to be our time. So we have all these different variables, and so now we're going to take a look at a couple of examples that deal with Newton's law of cooling.